Our next speaker is Vanessa Argueta. She is a technology professional with experience in database administration, project coordination, and data analysis. She holds a bachelor's degree in informatics from the Universidad Autónoma de Baja California and a certification in Microsoft SQL Server Administration. Currently, she is pursuing a master's in engineering and innovation at Citedi University. In her professional work, Vanessa focuses on maintaining data accuracy, optimizing processes, and supporting clients through practical and reliable solutions. She has participated in projects that require both technical skills and clear communication, ensuring that information systems operate efficiently and meet organizational needs. I hand over the word to Norma Argueta.
Hi, good afternoon, everyone. I'm here to share with you this project, Colors That Come to Life, application of deep neural networks on image colorization. And my name is Norma Argueta, and in company with Ulises Orozco Rosas and Kenia Picos, we have to explore the modern deep learning architecture. Deep learning architecture can bring life with realistic and consistent colorization. And please allow me, I feel a little intimidated to be there. How follow this outline and sorry. We have a brief introduction about this theme, CNNs, residual learning, GANs, peaks-to-peaks framework, visual transformer, hybrid architectures, dataset and training, the result and conclusion. Automatic colorization has become an important area in computer vision, and with applications ranging from historical photos and films, and improving medical image, and even enhancing creative media. The main challenge lies in the fact that a single grayscale image may correspond to several acceptable color versions. Traditional methods relied on manual cues or prior statistical data, but deep learning allowed us to learn colorization directly from data, resulting in far more natural and diverse outputs. And we are talking about CNNs, convolutional neural networks. And CNNs extract local spatial features through convolutional layers, making them ideal for detecting textures, edges, and fine structures. However, their limited receptive field can cause inconsistencies when coloring large uniform regions, like skies or background areas. This limitation motivates researchers to combine CNNs with architecture that capture broader contexts. And another method or architecture, residual learning. And Kaimin He and colleagues introduced residual learning, where the input is added directly to the output of a block. This concept helps the network train much deeper models without suffering from gradient vanishing problems. Residual blocks became fundamental for colorization systems as they enable models to refine fine details and maintain stability and during training. and Generative Adversarial Network, and GANs. GANs introduce the idea of competition between two networks, a generator that creates image and a discriminator that evaluate their realism. Through this adversarial process, the generator learns to produce sharper, more vivid, and visually convincing colorization. This approach improves both color richness and perceptual realism compared to earlier pixel-based methods. Pix-to-Pix framework, Philip Isola's Pix-to-Pix model was among the first to apply conditional GANs to image-to-image translation tasks like colorization. It combined L1 loss for accuracy and adversarial loss for realism, produce sharper and more natural results. This framework set the foundation for modern colorization GANs that focus not only on correctness but also on aesthetics and visual realism. And another architecture, vision transformers. And vision transformers represent a major shift in image processing. And they divide image into small patches and allow each patches to attend to all others using self-attention mechanisms. This global perspective captures long-range dependencies and contextual relationship, which helps maintain color consistency across large areas, something CNNs often struggle with. Hybrid architecture. To achieve both accuracy and realism, hybrid architecture combine these three paradigms. CNNs encode extracts local texture and age information. The visual transformer model integrates global semantic context, and the GAN framework ensures that the generated image look natural to the human eyes. Training using composite loss combine mean square error for pixel accuracy, adversarial loss for realism. Perceptual loss from a pre-trained BGG network for semantic quality, and total variation loss for smoothness. And balancing these objectives allows the model to produce colorization that are structurally faithful, semantically coherent, and visually appealing. The data set and training we use, we trained this model on tiny ImageNet and ImageNet, ensuring both diversity and scale. The training was conducted on a multiple GPU server with 4 NVIDIA Tesla V100 GPUs, converging after 50 epochs. Each epoch took about 80 minutes, and during inference, the model can colorize an image in roughly 0.80 seconds. This demonstrates that the hybrid approach is not only accurate but also efficient, making it suitable for real-world application. The result for this hybrid method, we evaluate the model using both pixel-based metrics like PSNR and SSIM. Our hybrid model achieved 3120 dB PSNR and 0.996 SSIM, outperforming baseline models. The result showed that the proposed approach preserve fine details and texture, produce vivid colors, and maintain semantic consistency across the image. Although this is still room for improvement, this finding confirmed that hybrid deep learning offers a strong foundation for future research in automatic colorization. And to the associated contribution to each component in our hybrid framework, we performed an ablation study, but semantically removing or replacing models. And for conclusion, merging CNS, GANs, and VTS, Visual Transformer, marks an exciting evolution in the field of image colorization. Each component contributes a unique strength. The CNNs enhance local feature extraction, and the GANs ensure photorealistic generation, and Visual Transformer provide global consistency. Hybrid systems now present the most promising direction toward achieving human level colorization quality, combining precision, creativity, and realism. So thank you for your attention.